We're live, I guess, right? Yep. Hello. Hello, YouTube. Recent stuff. Cool. Cool. That's good. Oh, shit. Or whatever. Anyways, what is the... Yeah. Good. Now, today we are continuing the streams on flow matching. I'm gonna just share links. Hopefully people start coming. Uno momento. Oh. Chat. That should work. No. Yeah. Nice stuff. Good. Okay, so okay, I guess we start. I will start since I don't know, maybe, but what was I going to do? Yeah, just reading this thing. Exactly reading this thing. Okay, so where was I? I was at this continuity equation, right? Yeah, okay, so hello يحلي خير يحلي شبس. How are you? I'm doing today this other course on flow matching and diffusion models. So yeah. Okay, so today we are continuing. I'm continuing this. نتابع اليوم هذا فاهمني حلي. نتابع هذا هو بالمينيكت ماريتي اصلا. تذكر ديسكورد ديسكريبشن شانل اللي تكليك الديسكريبشن تاع تجبر لينك ديسكورد والله الشانل اللي انت تخش كاع بس تخص الشانل بس تجبر يا سي يعني تخش الشانل تجبر ديسكورد راعي يا كان شوف لكم مباشرة. Okay, so I'm continuing this now. Let's consider flow model. Let us consider a flow model with a vector field ut with x0 following p in it, which is p0, and xt following pt for all t between 0 and 1, if and only if this thing. Okay, the continuity, the vector field is the vector field. Yo. يا حظي خيرت نورتنا فيك لباس
ما شاء الله نصلي فرنش ندخل معك. اوكي
problem man problem ان شاء الله sure Okay, so this is basically the continuity equation. Okay. So okay, this is the theorem. So theorem saying that if we have a flow model with a vector field ut that start in the that takes in the curve following this curve of probabilities following this vector field, then that then the vector field and the distribution verify the continuity equation. Okay. We can maybe say okay to that. For the mathematically inclined reader, we present a self-contained proof of the continuity equation in section B. Before we move on, let me check that. Okay, so this comes from the Fokker-Planck equation. Wait a minute. What is that stupid jump that happened? That just happened. Okay, slow down. Okay, so yeah, so the continuity equation is practically a solution to this where there is no diffusive part, where the diffusion coefficient is 0. When you have a diffusion coefficient being 0, then effectively this is the flow equation. Okay, that makes sense. Hello, Discorder. Who's that? Yo, long time. Did you hear me? Did you go? You hear me? Oh. I don't hear you though. Okay, so basically, yeah, they will. This is the proof of the continuity equation, which I will look into. I think I did look into it last time, but I will just refresh. Hey. Okay, so in this section we give a self-contained proof of the Fokker-Planck equation, which includes the continuity equation as a special case. Yeah, sure. When the diffusion coefficient. Oh yeah, just I can hear you just now. How are you? Long time and no see, no hear.
I can't hear anyone.
You can't hear me.
That's weird.
You cannot hear me. Oh. I think Discord was showing me. I don't know. Oh shit. Oh, though I'm not sharing my screen. Forgot to share my screen.
Hello.
Hello. Can you hear me?
Yes, I can hear you now.
Great.
I had an issue with my microphone for.
Yeah, okay. I see. How are you? Long time no here. No see.
Yeah, long time no see, no here. I'm doing well, alhamdulillah. How about you?
Great to hear. I'm good. I'm good. I'm good. I'm here with this for this stream. I'm doing this flow matching and diffusion models course. I'm following it, and now I am in like page 19, I guess, or something.
That's cool.
Yeah.
That's really nice to see. I don't know how long have you been away from streaming?
It's been like 3 weeks or something. Long time.
That is a long time.
Yeah, definitely. Long
I'll
time.
be like working in the background. I also have a project I need to present tomorrow. So
Good luck, good luck, good luck. Wish you the best.
yeah, thank you so much. So I'll be here.
Okay, glad to have you here. Okay,
Yeah.
enjoy. Good luck to you.
Sorry, by the way.
For what?
But I don't know if I told you about the Odyssey. Did you watch it?
Not yet. Yeah, you told me about it. You
Okay,
told me
so
that
you're gonna
you.
watch it.
I gotta watch it. Because why?
If you have time, obviously. If you have time.
Yes, well, I will probably watch it because I watch every Nolan film.
Yeah,
It's
it's
something.
actually really nice. Okay.
Did you watch it? Well, did you watch it on the IMAX actually in theater, or?
Okay, I was asking Cloud because I've never experienced the 4DX, and so I had like two options. Should I go for the IMAX or should I go for the 4DX? And I wanted the 4DX. It was a nice experience for me. So
You watched it in the cinema?
Yeah, I watched it in the cinema, but you have options. So
I
the
see.
4DX,
That's super
you get
cool.
to- It is so cool. Like for example, you get to feel the wind.
Yeah. I understand the guy. Even in Tenet, you notice it, but the loud music in Tenet, he likes to make big things, you know. Do you know that the plane that was crashed in Tenet, that plane? Do you remember it?
Yeah, I remember.
That's an actual real plane. He bought the
Yeah.
plane just to crash it.
Yeah. Some people were saying it was unnecessary because it like this
Yeah.
works without
No line is something. No line is
He
something.
loves to exaggerate things.
Is
But yeah.
I'll definitely watch
Okay.
it. Okay.
So,
Okay. Good luck. Good luck. Good luck.
thanks you too.
Thanks. So what was I? Yeah, focal Planck equation. Okay, let PT be. We stress that this document is necessary. That this section is not necessary to understand the meaning of this document, and it is mathematically more advanced. If you decide to understand where the focal Planck equation comes from, then this section is for you. Let PT be a probability path with P0 equals to P in it, and let us consider the STE x0 following P in it, and dxt equals to ut dt plus the standard thing. This is the focal Planck equation, and let xt be and then xt has distribution pt for all t between 0 and 1 if and only if the focal Planck equation holds. Oh, okay, this is the focal Planck equation. This is just the general. This is just an almost general STE because yeah, we are having here some kind of vector field and a coefficient depending only on t and not on x. Okay, so not on actually the value of x at the instant t, and this other thing depends on both x and t. Okay, so the focal Planck equation is yeah, this is an if only if so there is some kind of correspondence between the two, where this thing doesn't have the random variable formulation. This is just a differential equation in the distributional sense, I guess. If maybe not. I don't think so. Maybe it can be. whatever. That's not a big issue. Anyways. Okay, let's go back on track. We start by showing the focal Planck equation is an necessary condition, i.e. if xt follows pt, then the focal Planck equation is fulfilled. Okay, the trick of the proof is to use test functions. I know what a test function means. We use the fact that for arbitrary integrable functions, okay, okie dokie. In other words, we can express the pointwise equality as equality for taking the integrals. The useful thing about test functions is that they are smooth, i.e. we can take gradients, in particular, okay. Okay, let's go into the meat of the subject. Okay. Oh yeah, I remember what you did here. There is a term that will vanish at some point here, and you will get the image. My hand is a bit okay. I'm back. So where was I? Damn. This is the thing about yes. Okay, let's proceed with the proof. You're writing it as a discrete form without either dxt, and why is that? What does that h do there? What does that h do there? Okay. Okay, so this is just it is very hand wavy, and I don't like it, but we can continue. We can then take the following calculation. We can then make the following calculation. Okay, so what is the following calculation? Okay, that's a no problemo. That's a no problemo. And this is gonna just be the gradient in the direction of this thing. Yep, exactly. Yep, okay. And plus 1/2. What's that doing here? Okay, so this is he's doing actually more than the simple gradient. He's taking the full Taylor expansion, and here we have 1/2 of the Hessian, and he's leaving the rest. Okay, yeah, this is the Taylor approximation. Okay, and Yeah, he's expanding stuff here. Wait a minute. Okay, this comes from here. This comes from here. So this is just exactly the same first line, and this comes. This is where we're going to expand stuff. We will get h square. We'll get the 2 will leave, we'll simplify with the 1/2, and we will have this common cross term, and we will have the last term with the sigma square. Okay, that is clear. Now we shall note that the expectation, the conditional expectation, which is something I haven't wrapped my mind around yet, of the Brownian motion, the difference between the Brownian motion such that xt is equals to 0, and it is actually, this thing is actually following a normal distribution with coefficient h. Okay, that is acceptable. That is acceptable. Okay, so what we're doing now is just we're just basically composing this with expectation, with conditional expectation by xt, sorry, or some, I don't know how to say that properly. And stuff will start eliminating. This last term will vanish because of this thing. We will have just and this as well will vanish, and what we will have is just this thing, this first thing, and this thing, and the rest of the everything is going away. Am I right? Am I right or am I wrong? This is this, this is this, and this is okay. This didn't vanish actually. Yeah, this has stayed with h/2. What the hell? Well, in one we use the fact that e sigma t, e epsilon t is equal into a, yeah. But where did this come from? Where did this part come from? Where did that part come from? This did vanish, in fact. This has stayed, which is the second term. And let me ask the robots, the clanker, what's happened? What is a good model? K.6 usage. Damn. What happened to the last expectation? Why is epsilon there? Come on. Stop thinking, don't overthink. Hey. You're in a terminal. Don't use static. Use Unicode. Other than static. Not under. Yeah. Good job. Good boy. Okay. So. Right. Sorry. Okay. So. There is linear in dice because sure. That kills two terms outright. Okay. They vanish. Okay. Wild card. Okay. Ah, yeah. Okay. Ah, yeah. This has expectation 0, but it has what is it? It has variance h. So we will have here actually wait a minute. Wait a minute. So that's kind of a variance. But what did you do with these gradients? That's something I'm not sure about. So we factor out the variance by scaling, right? Ah, okay. Ah, okay. So you kept it as is, and yeah, okay. This is completely acceptable. Completely acceptable. We can accept that. And this stays identically the same, and this is replaced by the trace. Use the fact that what the hell? For any matrix A and sigma, that thing is equal to the trace. The expectation of is equal to the trace. This thing is not determined. What do you mean? Why? Why? Here. Because basically when you this is not at all trivial. This is not at all trivial. Okay. Okay, sigma I, sigma j. Ah. Okay. Interesting. You can accept that for now. Yeah, there is something that is bugging me. What is the this expectation thing? Oh. Yeah, this thing is not so clear also. Why? Ah, okay, okay, okay. We're in one. We use the fact that this expectation thing. Okay, and in two we use the definition of depletion and the Asian matrix. Okay, so what is that again? Yeah, okay, so this will go this will give the adaptation because you're just taking the tracing of the Asian, which is indeed okay, sure, sure. Shit. Gain. Gain, okay. Where am I? Where am I? Um, okay. Okay, so now we are taking the derivative, which makes sense, which is fine, which we can accept, of course, you can do that. You can do that. Beautiful. Beautiful. Okay. Okay. That is fine. That is fine, of course. And that is, of course, fine. And that is okay. Still, I don't understand. Okay, sure. You use this last calculation. You get some stuff simplifying. You get this, you get this, you get that. This vanishes. And you get what you want, actually. You get that integral with that thing. And this actually will give you the exact thing that you want because of... Yep, good job. Good job. Bien fait. Good game. We're in one. When you know, with the assumption, with the assumption that PT as the distribution of xt, still they wrote badly, which is nice in this age of AI. It indicates that they actually wrote this by hand. And in two we use the equation. Okay, note that. No problem, no problem. Note that to use this, we require integrability of the product. Okay. Okay. Where did I miss that? Sure. Sure. No problem. Note that this condition almost always holds in machine learning, both in data and functions because of numerical position limits. Therefore, it holds that. Sure. 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 Okay, this completes the proof that the focal Planck equation is a necessary condition. Okay, so if it is yeah, if the SDE that SDE is verified, then we will have the focal Planck equation for the distribution and the vector field. Now for the other direction. Okay, this is what you will tackle here. The focal Planck equation is a partial differential equation. More specifically, it is also called a so-called parabolic partial differential equation. Similar to theorem 3, such differential equation have unique solution given the initial conditions. So yeah, since it has a unique solution, then that's it. And since you can the solution can verify this equation, then it is the only solution. That kind of makes sense. It is a correspondence because you have a unique solution, so you just have you just had to verify this thing, that equation, and boom. Am I right? Am I right though? I don't know. I don't know about that. Now, if equation 1 holds for PT, which is shown above, that it must hold for distribution QT and of xt. Okay, in other words, both PT and QT are solution for parabolic PDE. Further, okay. No. Wait a minute. Further, we know that the initial conditions are the same. But construction for operating probability path. Hence, by uniqueness of the solution of the differential equation, we know that PT equals to QT for. So this is the argument. This is the argument, and I'm still not. It's not clicking to me, but I can accept that. I can accept that for the moment. For the moment, we can live with that. Of course, we're coming back to it. What is the thing? What is the thing? Here it is. Okay, so let's go. Let's move on to some exciting stuff. Yes. Okay. Note that theorem 11 is not converted from the local Planck equation where sigma t equals to 0. The additional. Where am I? Where am I? I think I was somewhere else. I was at the continuity equation. Okay, maybe I missed that. Oh shit. I have a problem with this thing. A stupid problem. And what is it? What's the thing? Zatura. Come on, Zatura. Split that one. Zatura. Come on, Zatura. Everyone is up to date. Everyone is up to date. Yet there are bugs. Super sad. Anyways, let's continue. Yeah, I did that. Stole that shit. Okay. We got him. We got all of that. That's fine. Okay, so Now before we move on, let's try to understand intuitively the continuity equation. The left-hand side is the derivative, the time derivative of pt, the distribution, describes how much the distribution at x changes over time. Intuitively, the change should correspond to the net inflow of probability mass. For a flow model, a particle xt follows along the vector field ut target. As you might recall from physics, the divergence measures a sort of net outflow from the vector field. Therefore, the negative divergence measures the net inflow. Scaling this by the total probability mass currently residing at x, we get that the net minus divergence of pt ut measures the total inflow probability mass. Okay, since probability mass is conserved, always integrates to 1. The left hand and right hand side of the equation should be the same. Okay. Now we proceed with a proof of the marginalization trick from theorem 9. Okay, marginalization trick. Let's see about that. From theorem 9, proof of theorem 9. By theorem 11, we have to show that the marginal vector field ut target as defined as in equation 18 satisfies the continuity equation. We can do this by direct calculation. Okie dokie. That's a no problemo. And wait a minute. What did you do there? Where did that pt come from? Okay, you multiplied by it outside. And okay. Where okay, d'accord. Je vois. Into we used okay, I see. By the beginning and the end of the above chain of equation shows that the continuity equation is fulfilled for ut target. By theorem 11, this is enough to imply equation 19. We are done. By theorem 11, this is enough. Ah. Okay, so passage تشغل فيه continuity equation. Use the continuity equation in the midway. Interesting. I did not expect that. Okay, this is interesting. I'm getting notification text. Learning the marginal vector field. Now we are ready to describe the training algorithm. The goal of a flow matching is to train the neural network ut theta such that it equals to the marginal vector field ut target. If this holds, we know that the endpoints x1 following p data have desired distribution by theorem 9. In the following, we denote unif by the uniform distribution on the interval 0, 1, and by e the expected value of a random variable. An intuitive way of obtaining u theta, which is an approximation with u target, is to use a mean squared error, i.e., to use the flow matching loss defined as this thing. Okay, the expectation where t is uniformly picked from 0 and 1, following the uniform distribution, right? Is that the way they say it? Okay, and x following the distribution pt on the data space. Is that me on the state space or something? Right? The distribution of the data space or some. What do they call it? They precisely they have given names to everything. It's just me that I'm not remembering stuff. The interpolating, I guess, interpolating distribution between the data distribution and the target distribution. Is that what we are doing, right? Okay. Oh, right. Is that well done? This is study work. Okay. Okay, let's continue. Whatever they call it. Okay, this is the last. It's defined this way. It's the expectation between the UT, the neural network, and the target thing, the target vector field, which is of course what the hell? Where do we get this thing? This is something we don't know, and this expectation is identical to picking x from the data and z from the data and x from a marginal distribution. If they call it that way, again, I'm not sure. Where pt is equals to the integral of pt following the conditional pt times the p data x t p data z dc is the marginal z also in the first one, is the one being conditioned on, is the marginal probability path. And okay, this is the marginal thing, and this is the conditional, I guess. Okay, and in one We use the sampling procedure defined by equation 12. Yep. We talked about that for some time. Intuitively, this law says first we draw a random time. Second, we draw a random point from our data set. We sample from the conditional distribution at time t, conditioned on z, e.g. by adding some noise, okay, and compute the neural network, okay, because we have now t and x. We have now x, which we did sample from that thing. Finally, we compute the mean square error between the output of the neural network and the marginal effective field, which is, I don't know how you get that. Unfortunately, we are not done here. Well, we don't know the formula, yeah, as I just said. By theorem 9, we cannot compute it efficiently as the integral is intractable. Not that he keeps saying that integral is intractable. It's that you don't have. It's that p data is you have just discrete points of p data. And another thing, what does this even mean? What does this even mean? Yeah, I don't know. Instead, this is from a theoretical standpoint. It is as solid as any theory, but it's not real. It's a woozy. Well, we do not know the formula for U targets by theorem 9. You cannot compute it efficiently as the integral is intractable. Instead, we will exploit the fact that the conditional velocity ut target is tractable. Excuse me. Yeah, I remember something about that. To do so, let us define the conditional flow matching loss. Ok. Okidoki. D'accord, pas de souci. Note that the difference between equation 24, we use the conditional vector field instead of the marginal vector field. As we have an analytical formula of ut target. Okay, we can minimize the loss above easily. But wait. What sense does it make to regress against a conditional vector field if it's the marginal vector field we care about? What sense does it make to regress against the conditional vector field if it's the marginal vector field we care about? Yeah, okay, solid question. Let's see what's your answer. As it turns out, by explicitly regressing against the tractable conditional vector field, we are implicitly regressing against the intractable marginal vector field. The next result makes this intuition precise. Okay, let's see about the next result. Theorem 12, the marginal flow matching loss equals to the conditional flow matching loss up to a constant. That is the thing where C is independent of theta. Therefore, the gradients coincide. Really? Okay. Surprising. That is indeed surprising. Here, wait a minute. Attends une seconde. Il y a des choses qui sont pas assez claires ici. Ooh, I don't know why that is possible, but let's continue. Let's see. Wait a minute. Okay. Hence, minimizing the conditional loss with e.g. stochastic gradient descent is equal to minimizing the other thing with the same fashion. Okay, pas de problème parce que the gradient is the same. What a joke, what a sick joke. In particular, for the minimum theta star of the loss of the conditional flow matching, it will hold that. Okay, i.e. the neural network will equal to the marginal vector field. Okay. Assuming an infinitely expressive parameterization. Yeah, you don't need to prove that because the gradient are the same, I guess. Oh, let's see. Maybe I'm missing something. The proof works by expanding the mean square into three components and by removing. Okay, the proof of the equality of the two things up to a constant. Okay, let's see. Okie dokie. Yes. Okay. Yes. Wait a minute. This is the constant. You add the other constant, but what do you do with this one? What do you do this with the gentleman right here? What do you do with it? Okay, that's that. المقالع وخي شرفتونا سيادة الشيخ الكبير في الحال. هذا كورس ل MIT ل flow matching diffusion. وتشوف نتفاعل مع كورس راك تعرف page 20 في البحث progression. هذا ستريمي عندي انه ستريمي thing. I guess this is the third or fifth stream or something. ستريم الرابع اخبار هذا الكورس. وفيه نفس الوقت فيه لابس فيه what is it فيها notebooks. okay. فيهم exercises implementation الكورس. وتشوف نقرا كور يعني الحق بارتيسيبيت نعدل لاب. فتعدلت لاب فتوفيت لاب واحد منهم في ستريمات الماضي. وقتها عندي لين افانسي شوي للاب ثاني. في 3 لابات. where is it؟ في 3 لابات. انا الاول عندي وقفيته. مسائي الثاني ونفت دخلت حاليا اليوم فتوى في كور الاول كان في لاب stochastic differential equations OTEs implementation simulations وداك الشيء. راكتيها في الثاني ما دخلت بيه اللي مست نقرا عن flow matching شنو هي والالغوريثمز شنو هو. دونك حاليا موجود في الحلقة الانتباه. and that's it. راكتيها في باج 20 يعني page 20 يعني almost here. في 19 هنا ثيابها yes here. وتو استريميت عايدا عن شين قالوا انت كما تعرف عندي ايميلات وكاتب الشيو يا خير لوها بنفس الاسبوع الماضي الاسبوع السابق ما استريميت بي اللي كنت متبارك مع نعدل بيبر نعدل ذاك الاخبار. وذا هو في كل ويكند نتبارك مع ذا ونعقب ما نوفي اخبار ايميلز ولا شيء ونعودوا ملي ما ستريميت. دونك اتيز لوز من قد عني ما ستريميت ما كون كل ندورو فيه باسرع وقت ممكن. ياك نعود نقد نعدل بشيء المره اخرى يفتح لي ان شاء الله وقت ثاني. فهمتني؟ دونك اخترت نعم يسوى اللي يخلق نعدل كونتينيو ستريمز اللي نعم لين وفي بدل من عني بدل عني بلوك هي ما ستريميت بي اللي عندي امور خريات. فهمتي؟ whatever it is the case I should continue working on this thing to finish it. Otherwise I'm not gonna finish. Otherwise يتم weeks go by, stuff go by. ستريمينغ فايت بيلي انا حرفيا انا ارانجاني قاسم روايات خارج قاسم شي انا فونسيتهم كيت باغ اكزومبل راست لونجاج انا كنت تختار نعرف وفيت كورس راك تعتقد نمبليمونتي بها المور شويه نعرفها وحرفيا اتس بيكوز اوف ستريمينغ بيلي انا خارج ستريمينغ يقعد عندي اسم ورقتين عاد ما بما ان عندي ستريم ذاك واش كذا ذاك فيكس فهمت هادشي ذاك هو فريمون قد نوخر منه كونسيستنسي توخر لك نتائج سيرتو انا اللي ما تنوض لاعب صح مثلا عندي كور يفضل لي انا لاعب ولكن تايمز فلايز اللي ما تعدل شي مبرمج شي كدو بروجريشن تعدل شي compound. Okay, let's continue. I hope that makes sense. I get to be really أخبار that thing that documents اللي كان تنجز كنت مع أخبار. Anyways, let's continue on this thing. Okay. What did they do here? Yeah. Okay, so this thing is okay. This thing is أخذت الله يبارك فيك الله يبارك فيك شيخي. This thing is this thing is okay, of course, no problem about that. This is just the minority of the expectation. And this thing, they said it's a constant. Constant in what sense? In what word it is a constant? Yeah, it doesn't depend on the parameters. Okay, here we are calculating here the loss function, which is okay, no problem about that. So you still have this to deal with. If you replace this by the marginal one, which I think is doable because they are related by some kind of something. Let's see. One holds by definition, 2 holds by formula. Okay, no problem. 3 holds. In 3 we define a constant C1, and in 4 we use the sampling procedure of what is 4? What did you do here? Okay, you changed this. You changed this thing. Yeah, okay, no problem. That is no problem. No problem about that. Of course, I did this the last time, but I'm having a bit of it's not super fresh in my mind, but it's okay. I remember the thing that was being done. Some a vague remembering of it, if that makes sense. Anyways, where was I? I was here exactly. عندي مشكلة في I have a problem with this PDF viewer or something. It jumps from time to time. What's the best PDF viewer? Anyone one? On Arch, if that makes sense. Minimal one. I use Zathura with that thing, but it jumps unexpectedly. Check online. Press forms. Okay, okie dokie. By the way, I'm using this thing. You guys wanna see what I'm saying here. Okay, so what is this let us re-express the second cement. The second cement. No problem. Yeah, this is the thing that I was talking about. I'm guessing they will use this kind of a trick like this. You get a triple integral, and you will get. Uh-oh. Uh-oh, I didn't expect that. I did not expect that. Ah. Interesting. Okay, cool. Okay. برافو عليك. برافو عليك. That's acceptable. That's acceptable. But I'm still again having issues with this, with the meaning of this. But yeah, I think this will convert. This thing will convert. No, it cannot. It cannot just convert right away because you have a z here. Cannot just do that. This actually depends. This expression actually depends on all of the variables here, on z and x and t. So you cannot just do some kind of simplification or something to make it go back to a form like this. But I guess, yeah, it's okay. It's okay if the product here represents actually a distribution in itself, which is I don't think so. I don't think it does. Yeah, that's weird. That's weird. Let's see the commentary here about it. Where in one we expressed the expected value as an integral, and in two we use equation 12. What? I'm coming back. خلينا نقبل المهم نرجع. Yo, I'm back. Let's see. What? Okay, so what did they say? In one, we express the expected value as an integral. No problem. In two, we use the equation. Yeah, okay. I see what you did there. This is just the exact expression of ut. by definition. Is that by definition again? I guess it's no, it's a theorem, and it is. We did prove it. We did prove it using the continuity equation. Yes, we did. In particular, x1 is the following follows p data for this ODE, so that we might say UT target converts noise into data. Oh. 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 This conditional thing is just let's backtrack. Let's backtrack to stuff. Question. What is that? الله ما انا ادري شنو. شوف احنا نقبل بي اف ريدر انا 20. It jumps just non-point. It snaps page boundaries. It triggers with mixed pages. Yeah, if you want something similar but minimal but without jank, the usual picks on Arch are. Hey, yo, use Markdown for tables instead in writing instead. Yeah, ما تنشي صالح. Okay, LLP. Yeah, okay, this is okay. Let's try LLP. شوف LLP شو ماسي. داني نبدل PDF viewer. I'm changing my PDF viewer. LLP. It is LLP, right? LLPP. And it is not in the standard. Okay, paru. Let's see. Okay, let's read about that thing. Let's read about that thing and see if it is something legit. Let's modify is that thing. Kamal come in. LP ultra minimal vim keys now. Okay, that's not what I want. Free papers, textbooks, heavy and Zora, keyboard different smooth scrolling, what's the latex sync, format palette, no paste snap version. Got a Seok. Let's see about Seok. Okay, let's see. شوف Seok كانوا نافق. We can preview jumps reference bibliography. That's cool. I mean, this Seok thing kinda cool. But it looks a bit UI. I don't like this bottom line. This yeah, but it seems to be not so bad. Let's try it. Seok. Okay. Famous Seok. Okay, خلينا نستعمل Seok. Where is it? Where is it? Where is it? سيوك. سيوك مو خارج. أخبار شني؟ الأخبار شني؟ What the hell؟ ممسحة. فاروق SS. سيوك جيت. هاد implement حد بعطه اسمه. Okay, so let's see the things here. سيوك Okay, let's see. Let's see about this. Hopefully we don't get hacked. I hope so. Let's try to not get hacked. Okay, so this will get this library. We have this ads. And what is the link? شريم هو صاحب سيوك والله ما صاحبه. شريم صاحب سيوك don't that looks better. That looks okay. That looks okay. شريم صاحب سيوك. Okay. Pas problem. Okay. But there is something here. Ok. Vas-y. Installe-toi. Installe-toi, s'il te plaît. Optional dependencies for 56. Semi-porter plugin. Ok. Pas de problème. Ok, we are git cloning it. بعد نقول اللي عندنا عنها لانجاج ما نعرفش يعني يريد كود 100 سنة. C. Based. That is based. Let's go see. Compile fast. Compile fast. Please compile fast. Anyways, أنا تنظن نرجع اللي مهمة عندنا. وين مع ولا جامبي بي أنا تنافيكي PDF ريدر تلما تعبان. خير من فرا وبعض دوم قلعوا راك. خلاص وقتش مازال منه. Where was I? We're getting really sidetracked here. Let's go back on track. Okay, so note that this was really the crucial step of the proof, which is we express the integral as expected value in 4. Yeah. The beginning of the equality. Okay. T from uniform, this one from the data, and this one from the. So this is what they are doing. This is what that expression means. Yeah, of course. Sure. I was being ignorant. That's on me. Note that this was really the crucial step of the proof. The beginning of the equality used marginal vector fields. Used the marginal vector field ut target, while the end uses the conditional vector field ut target x such that z. Okay, we plug this into the equation of LFM. Pas souci يدير له تو كونستان ثاني ما عندك مشكلة. مرة ثانية لا كونستان plus ou moins way classical mathematical trick, classic trick of the trade. And yep, pas de souci. Yep, this can finish the proof. Therefore, flow matching training consists of minimizing the conditional flow matching class. Nice. Pardon, I should make an extension عني لأن يوفو هاي وقتها لين يستوي يوخل progress يوخل هذا بعض اسمه. Yeah, I should make that one. Let me do something. Okay, so Oh shit. Oh shit. Oh shit. راني شعلني هذا وقت يا. Oh no. كونيكسيون ضعفت. وي بيت كومبيلي رواية. يو. اوكي cool. Watch Tmax scratch window session from time to time and notify me with notify send when the compilation when LLPP gets installed. Finishes install. I've already yo, look at this if you are here. Hey yo, watch the Tmax session on Scratch, and when the what is it, LLPP finishes installing, I've already sent it. Not LLPP, Sioic is the one that I've installed. If it finishes installing, send me a notification with notify send. Okay. Look at that. Look at that. It is so bad. Sioic. Look, look at this. If you're the Tmox on Scratch, and when the Sioic finishes installing, oh yes, it's S. Let me. Notify me. Notify me with notify. عندنا قاعد تلقى تلقى installed. I've already started the installation. وقع. Okay, let's try this this new Sioic. Right. Okay. انترفاسك كح يا غير. Way Mandelbrot. Let's go. Okay, so this looks actually like something nice. Let me sign this 3 minutes here. ولدي نقول له quelque chose. I've installed Sioic. Configure to me a decent config file for it that matches my theming. Check check.config.tmax./minimal.conf. That's it. Theme minimal. D'accord. Yo, no. خايبك لا تردح فيها وقت فيها تعدلي رواية ما أعرف شنو. لا كون كيس اللي بك الأخوة. anyways حنفتحه Sioic lecture notes. beautiful. يفتح لك something ديجا قاعد. اوكي Now, okay, now this makes more sense. Sync. Okay. Check. Let's config. Back check stuff. Up. So let's continue on our journey. What is this? What is this? That's bad. That's not good. Reload. It. Also use zipcar. Cont. Check. That's bad. Okay, let's continue عنا بايك خمرك بايك بخمرك اها زبانة هو اسمه ما ترشع والله سيكريست. شيء هو قال له عنه من لمر دي سنة في عنك قد تقبل papers قد شامبي شاب والله خلط راسنا shit I'm still picking my stuff let's go جنبت. اوكي سو على كل نرجع للمهم لا نتابع دون نفكس القضية اوف ستريم نعرف الشحن شو والله تبي اشوف هاي الرواية It's a lot of options man استحفي وهذا whatever let's continue on our stuff therefore flow matching training consists of minimizing the conditional flow matching loss. Okay, the training procedure is summarized by algorithm 3 and visualized by figure 7. Note that there are several striking features about this algorithm. First, we never actually simulate any OD during training. Okay. People call this feature simulation free. Of the algorithm simulation free. This makes training extremely cheap, and you don't have to roll out trajectories of the ODE during training, which takes a lot of steps. Second, the training is simple regression objective. It's a simple regression objective. We use this. We are just regressing against the UT target. See, so it's not too different from the supervised training at all. Finally, the algorithm is extremely simple. It's hard to think of a much simpler objective, training objective. All of this makes flow matching an extremely appealing method for large-scale machine learning methods. Once COT data has been trained, we may simulate the flow model. Okay. Via EG algorithm to obtain. Okay. Looks like we're getting a lot of algorithms dropped in sequence. This is algorithm 3 and that's algorithm 1. Damn you Zathura. To obtain X1. This whole pipeline is called flow matching in the literature. Okay. Interesting. 25. 27. And 26. Let us now instantiate the conditional flow matching laws for Gaussian probability paths. Algorithm 3. Okay, algorithm 1 is we've seen it already before. Okay, this is just yeah. Okay. We were sampling here from this algorithm to simulate. Yeah. Sure. Taking an initial random thing and you making it go through this flow function. Yeah, interesting stuff. Now let's see the big algorithm. Algorithm flow matching training procedure for Gaussian conditional OT path, cont OT path. That OT I think is optimal transfer, but let's continue. PT XZ is equal to mean TZ and variance 1 minus T squared. Require a dataset of samples data neural network PT. For each mini batch of data, do sample example Z from the dataset, sample random time uniformly from 0 1, sample noise epsilon, and d-dimensional noise vector. Question, sorry, and set X to be an interpolation point between the segment of Z and starting from the noise to the data points. Okay, and we compute. Okay. Interesting. That is interesting. What is this thing? Irrational. Why do we have this? Okay, because we will differentiate. Okay, so this is actually just this is the derivative, the time derivative of this thing. Okay, so it's following the gradient of this. Okay, hard to see. Oh dang it! That's a huge gray box. Nice fun, nice stuff. We gotta move on because we are a bit late to the party. This doesn't work. Okay, so I cannot move unless I finish I finish this section that I'm in, and I finish the other section as well. Okay. Which is 3 pages or even more. Not 3 pages. Yeah, I need to finish that as well. Oh, I've got a lot of stuff to dig through. This is still the beginning. I don't think I'm ready for. Nonetheless, let's check. Let's check this thing. Source. Marimo edits. Left. Okay. Noise. Yo, you still have people on YouTube? Or no? Yeah, people left. It's okay. It's okay. It's fine. Give me back the light mode. That's sick. That's good. I like the when stuff are on the command palette, because that where things should be. You know what I mean? We'll go back to that later. We'll go back to that. Okay, so let's continue on this. Let me for a moment think. Oh, we'll back. Ayo. Dang, it's oh. What I want to say. Boom, 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 boom. Okay, so the buffer matching consists of minimizing collision formats, training procedures, which is down. Okay, we got that. Example 3, that's in. Yeah. Flow matching progression and probability path. Pass. Let us respond to the example of Gaussian probability path. PT. Z, which is equal to that thing. Okay. Yeah, remember that. Where we make a sample from the conditional path via this thing. Okay. The case that we had here is where alpha is equal to okay, no problem. Remind me again, what is the definition of this alpha and the definition of this alpha and beta? Okay, so here we have an explicit analytic expression of okay. Understood. Okay. 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 Builds this thing, which is, excuse me, sir. What is that? Okay. That's okay. Okay. One thing though, why you have okay. But you will have alpha z there over beta. But yeah, okay, over beta, which simplifies with the other thing. Okay. The simplicity of, not the simplicity of LCM. Yeah, it's not so complicated, but worry about those derivatives. Example of data. Well, you can do derivatives with the automatic differentiation, but it depends on the formulas for alpha and beta, which I think we did not pretty much specify. We did not specify. We specified them for some special cases, but for t, and the other one is 1 minus t, but yeah, and I remember. Okay. دين نصلي المغرب نرجع. لا عاد حد هنا تيها. Coming back guys. Be right back. We'll be right back. Okay, we will be right back. That is up, timer, whatever, and let's call 15 minutes. Let's call 15 minutes. ميتي اسم سيت صادقين نرجع ونسين ولا شغلتنا راحتنا ان شاء الله. Okay, clear. I'm guessing 15 minutes. 15 minutes. I hope. I don't know. Okay, peace out. Oh, oops. I almost, yeah, 20 minutes. I should have put 20 minutes. So we're back. We're back. Hey, viewer. What up? See Mochi. Okay, so let's continue the reading. And then, inshallah, we attack this, we attack the coding part. Okay, so, yeah, this part makes sense. You just use substitution. You substitute x by its value. And that's it. Okay, we're in one. We plug the equation. We're pressing 9. Okay, sure. Not the simplicity of LCM. We sample a data point z. Sample a noise. It's epsilon. And then we take the mean squared error. Let us make this even more concrete for a special case. Well, yeah, this is what I was thinking about. The corresponding probability is this one. It sometimes refers as the quotient cont OT. Cont OT. I think this is conditional optimal transport, but what does stand for? No. Where is your stupid flash? Come in. No, sure, come on. Optimal transport, yeah. Then we have alpha dot is 1 and beta dot is -1. So that, yeah, okay. So this is what I've seen before, right? No, it's not. It's not the same thing. It's not this. What I've seen before. I'm talking about this one. It's not that. It's almost that. Well, it should be. It should be it because we took exactly. It is the same x. So what's the issue here? Why it's not the same thing? Why it's not the same thing? Why isn't it the same thing? Oh, okay, yeah, it's the same thing. X. Okay, this is X. Okay. Many famous state-of-the-art models have been trained using this simple. I hate اللي ينقالوا زثورة لا ينقذك لا حنشوف أنا باش كم تزويد أوكي ورطنا خليتنا ودريتنا زثورة أنا مالي فويسي ماشي ترانكيل كل شي ماشي ترانكيل ياكلتو مجابرين من فوت الميوزيك داكور what is this? Okay, many famous state-of-the-art models have been trained using this simple yet effective procedure, e.g. Stable Diffusion 3, damn, Meta Movie Gen Video, damn, and I'm saying damn in a weird way, and probably many more proprietary models. In Figure 7, we visualize it in a simple example, and in algorithm 3 we summarize the training. We summarize the training procedure. Okay, this is the yeah. Okay. LaTeX. LaTeX. مشكلة the example السابق the example should be before algorithm. Anyways, okay. Illustration of theorem. Let's be serious. Illustration of theorem solve the question conditional OT probability path. Same thing already from a trained flow matching model. Okay. The data distribution is the chessboard pattern, top right. Top row histogram from the ground truth marginal probability path. Bottom row histogram samples from the flow matching model. As one can see, the top row and the bottom row match after training up to training error. The model was trained using arbitrary. Okay, cool. Okay, cool. Cool. Makes a bit of sense, but let's continue. Okay, summary 14. Flow matching training consists of learning the marginal probability field, field. To construct it, we choose a conditional probability path that fulfills P0 is equal to P init and P1 is equal to the Dirac mass at C. Next, we find a conditional vector field UT such that its corresponding flow psi T fulfills this thing, or equivalently that UT satisfies the continuity equation. Then the marginal vector field is defined by that thing follows from the marginal probability path, i.e. okay. In particular, x1 follows the data and for this so that UT target converts noise into data as desired. To learn it, we minimize the conditional flow. Okay. Let's read this again. Oh, okay. The most widely used example is the quotient probability path. For this case, the formulas become okay. That's the interpreting thing is a normal distribution. Okay. Good. Sure. We've proved this somewhere. Shamil. We beautiful. We finished this part. That's nice to see. That's nice to see. Now let us review this part, this summary. Okay, so flow matching training consists of learning the marginal vector field. To construct it, we choose a conditional probability path that fulfills the boundary conditions, okay, initial and terminal things of a conditional probability path. Next, we find the conditional vector field for this probability path, okay, such that its corresponding flow fulfills or it is or equivalently yeah, I mean it means just that this it's just that the marginal vector field I will review this. I think I have a grasp of it. I need to really put it down. Let me take a pen if I can make this stick. Let me make this stick. Let me make this a stick. One moment. By the way, do you have some new chats? Do you have a nice chat? No. Yo, viewer, you can talk to me. You can't feel free to tag in chat if you wanna ask anything or speak your mind. I'm not. You don't have. There is no interruption here. The objective is just to talk, chat, whatever comes to mind. Okay, so I'm trying to write this on paper, see if I, yeah, to make it stick, you know. I cannot just talking about it and seeing it. It doesn't really make it stick. Doesn't make it. I'm trying to find the place where I did things last time. Yeah, found it. Okay, cool. Super cool. والله أنا يفك. Yeah, I'm writing here is in a pencil, which is not so super clear. Okay, so okay. Bum, 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 bum. So shit up. So that was just me rambling and scrambling. It's not. Yeah. This other thing is. Sorry. Should I actually show you what I'm doing here? Maybe I should. Maybe I should. Maybe peut-être I should. If it's even clear, I don't even know. I'm not even sure if it's clear. Is this something clear? Actually, where's my phone? I can take my phone and let's see about that. Maybe that's something. Maybe that's. Yo, what was the answer here? Yeah, okay, no problem about that. Let me get Pro to get me stuff. What can I? بالمناسبة يسج ما ولدت in 3 hours. What is I want to show my camera in my phone. Link to show my phone camera in OBS for streaming. Find me ways. Find me the right minimal way. Right. I think there is an IP cam app. A cam app that streams app to stream to web stream camera mobile phone camera speed phone camera. I can yap to this, but my TTS is my STT speech to text is not so good. But anyways, I think there is a on camera to and then open it as a window, no base. Okay, let's see this what is it called? DeepSeek. Let's see, DeepSeek is the way. OBS Ninja. Ok, vidéo. D'accord. Ah, super. Add your room, create room. No. Wait, what the fuck? Really? No, I don't want this. I don't want it to be Oh, I can do something though. I can stream yeah, I can stream my camera and but I want something local instead of juggling around. Yeah. Oh, really? Really? Let's see if that's true. I don't think it's true. Je crois pas. Je crois pas que c'est vrai ça. Je crois pas. HTTPS pop-up video.ninja push. Not my front camera. I want yeah, this camera. No audio. No audio. And start. Let's see if this actually works. Video.ninja push GRDE and RPP. I think, yeah, I don't think, yeah, yeah. في بروسيسور latency over USB. Then in OBS. Oh, but yeah, I have USB-C. I have USB-C. Maybe that works. And then USB capture. Webcam. There is something called the webcam or whatever. This is taking time. This is taking time, Chad. What is it? The webcam. Let's try also open stream. See, yes, the name looks better. Okay, we're going with can I my Steam. Okay, it's fine, I guess. It's completely fine. I can. Or is it? Is it though? Yeah, it's fine. It's fine. It's fine. I will just yeah, no problem. I was thinking about something. Whatever. PC webcam, OBS camera. Whatever. Continue. We're using the app. Okay. We're using the app. Okay. Ok. 192. 100, 205. 47, 47. Tab, tab, tab take. Tab give. Wow. Still, والله شقاية برايم جن. Anyways. What the fuck? What went to... Okay. Are you kidding me? I don't wanna. والله فضيحة. The fuck? Cannot be fucking serious. كنت فكرة يا. Maybe it's scam. Sorry guys, but you know, for the quality of the stream, we will, yeah. This experiment will be nice, you know what I mean? Especially if I like find a place to. Nice. يا سلام سلم. يا سلام سلم. You see this? You see this thing? You see this craziness? هذا الله شو البعر حق مصحى دون شنو. What the fuck? Can you see my equations? فرضا نطيروا من هون. Yo, the rate cam is as. Find me an open source Android app for sharing camera in web. Look at no. Yo. But anyway, I think this works. If this works, it's gonna be epic. Trust me, chat. Yeah. I mean, beautiful internet. Beautiful internet. Oh, nice. I'm a professional streamer. Je suis un professional streamer. Oh, we got 27, only 27 views for all this time. Why? Why I'm having though one? Do I actually have one viewer now or 0 viewers? Because je ne sais même pas. Je crois pas. Je crois pas. Je crois pas. Je crois pas qu'il y a quelqu'un qui regarde. No. Let me get this out of here. see what can I do this. Streams. I got but only streams mp. How can I open that in the browser or window? Oh, wait a minute. Maybe in pig, maybe my boy called back. Okay, let's try with this bad boy. If it does it, MPV is a badass if it does it. Ah, this didn't work, man. Okay, now let's try other options. This should work like easily, and I'm not. Let's see about this. Should be it, yeah. Oh, perfect. That is perfect. I love it. I love it. J'aime bien. Let's even take it to this other guy. or even to MPV. MPV should cook it really good. Let's cook it well. Oh shit. Always on. Okay, so this works. Fuck. This is bad also. This is bad. tab.com / this thing. Let me get this. Hey, chat. Let me get this. Let me get this. Let me get this. I'm trying to connect my screen. At the same time, the state of the software now, the technology is really, I'm really rigged on the performance of my phone, because I believe it should be super fast, and it is not. scanning app. It's forcing what the hell? I hate this. It's forcing me to scan the app before this app. Restore. Okay, install now. Sure, go ahead. Cool. Rub. Okay, let's try this again. Okay, cool. There is a vibe coded app which is better, which is not bad. المهم عندنا شي اشتغل. Not take any vibe coded format. Okay, now can you see me? Not bad, not bad. Yeah. Let's stream it. Let's stream it from MPP. Yeah, don't شغله ده شغلت. MPP is the one that's having. MPP is the one that is ass. Whatever. Anyways. In time for your time, one time. Yeah, whatever. This way, this is great. Okay, let's add that here. OBS phone cam. Yeah, now I can add this scene here. And that will make it not bad. Will make it actually pretty damn good. What was that? Shit. Yeah, it's fine. Keep it there. I don't know, is this let me check the YouTube feed. Oh hey, does this work now? Let me check. Check my stuff. Is this actually okay? Is the camera seeable? I don't think it is. Anyways, let's continue. Nice. I don't know if it is viewable yet. Ah, okay. That looks a lot better. That looks a lot better. I can actually write here. Okay, good. Okay, let me switch that and make this like this. This is looking a lot better now. Okay, let's continue. Let's continue. Okay. Stuff I should know. Oh shit. Okay, that is not captured by the camera. Not reachable. So okay, so this is my line. The rest is not okay. So anyways, what I have here is simply and I have upstairs. Okay, but can even move it a bit up to make it maximize any space. Yep. Even it's okay. Okay, good. Okay, anyways, let's continue on this. I think you see everything now. You see everything now, I hope so. Bismillah ar-Rahman ar-Rahim, where was I? Yes. I'll read this summary again. The class consists of learning the mushroom field. To construct it, we should choose a condition priority path that fills P0. Okay. Next, find the conditional vector field UT target such that the corresponding flow fulfills the thing. Or equivalently, okay, so shit, I moved the thing. I hope things are okay. Okay, good. Can I, for example, rotate this? Can I rotate C in OBS? Okay. So that way. My writing here will be upstairs. Okay. Let's pick a transform. Rotate 90 degrees clockwise, which should be what I want, right? Classic affected situation. Let's do that twice, and I should be just fine. Move up. Transform. I can even transform this even more, I guess. I can Very slow. Super slow. Okay, good. Yeah, that's okay. That's actually more than okay. That's phenomenal. That's phenomenal. Yeah. Okay, good. Now I can simply write here, right? Right. Should be able to write. Come on. Come on. Oh shit, there is a microphone. Okay. Yeah, mute that thing. And I want the camera to get back. What's happening? Am I playing it somewhere else? I'm playing it here. Okay. It's actually the mic is better here. Maybe. Damn them apps. So Ipcam for some reason is super slow. For some damn reason. It doesn't zoom also. So what I'm doing here. Oh, okay. It even. Okay, not bad. Not bad for a stupid Ipcam. Not bad. These things really did tire me out. It really did. Now let's rotate this. Okay, so we'll rotate it. Yeah. Okay, clockwise. Okay, good. I hope this is. I hope. Yes. Hope that's yes. That yes is readable. Okay, anyways, now we go back to business. Simply take my thing back, and my thing will be not so bad, not so bad. So what I want to do here? What do I want to do here? Okay, so full matching training consists of some people are back. Oh, will be back. How much time did I stream? 4 hours. Okay, it's not bad. Full matching consists of going back. Okay, cool. Okay, so what we have here, we mm, Full machine training consists of learning the marginal vector field, okay, which is done by which is represented by a neural network. To construct it, we choose a priority path, a conditional priority path. Okay, that fills. So the goal actually is to is to learn UT target. Okay, but the goal is to construct UT target. So to that goal, let's focus on this. PT of XC is taken. We choose this PT such that P0 XC is equals to the random. Okay, and P1 of dot C is the derived function. Okay, so this is what we okay. We choose one that verifies this, and we find a conditional vector field that it's corresponding that actually there is a and you see XC that is compatible with PT. Compatible here is either that the corresponding yeah. Its flow or the continuity equation, or that I recommend that UT target satisfies the continuity equation. Okay, and then let me come on, stupid ad. Let me because that's I believe we mean that this satisfies, because until now we didn't construct PT actually. Okay, which we don't want to construct either, huh? Or did we? Yeah, no, I have this PT here, No. What the hell it? Uh-huh. Okay, the marginality is this one. It's taken by exactly this. This divided by mass. So it's this is actually a density because its integral is 1. Yeah. Of course, with respect to z. Okay, then here and basically UT target will be equal to the UT target xz et xz p data over of z, of course, right, of pt x dz. Okay, you will just weight across all data points, across all points z. Okay. Oh shit. Are we live? Should be back live, right? I got to be. So shit. I'm on a USB-C port. It's not supplying power. I'm activating my charger for my phone. Just wait a minute for me, guys. Shit. Anyways, looks like you're not getting. Oh, wait a minute. Whatever. Oh. Oh, nothing. There you go. You got some views in my little thing. Mhm. Yeah, the word c'est pas la belle quand même. Okay, so okay, so So this last thing follows the marginal priority path. Okay. Whatever, guys. Let's not bother so much about this, because yeah, I'm leaving it. And I think I will end the stream here, because we've reached a nice sweet spot. And yeah, next time we revisit this last part, and we do the score matching, whatever. Okay, this was good. This was enjoyable. I did like 1, 2, 3, 4, 5 pages. Well, not so bad, and peace till next week.